Hey folks, welcome out there. Hey, there's two of us again today. 1, 2.
That's
and
right.
Gary Petco's back with me today. We want to hear from you guys, all right? Yesterday we kind of had a little slow day, and it's okay. But we want to hear from you guys. Give us a call at 844-686-2378. Now, I know some of you haven't been to school today because it's election day in different parts of our state, and some schools were out for students and such, but we still want to hear from you, all right? So, and adults, you've been working, right? So go ahead and give us some calls out here. We would love to hear from you this afternoon. Gary is our, supervisor of mathematics,
yes.
at Knox County Schools here in Knoxville, Tennessee. And I rely on him a lot for a lot of things, and he's good to be here today. And we'll see if we can put our heads together and answer a lot of your questions and your problems. If you just give us a call. Once again, that number, 844-686-2378. Hearing the phone ring now, let's make it ring more and more, all right? And while we're at it, Gary, you ready for problem of the day?
I think we've got it.
Let's go problem of the day. Let's see what we got. Read on, my friend.
Okay, we've got a triangle problem. The ratio, back to ratios. The ratio of the measures of the angles of a triangle is 3 to 4 to 5. Find the degree measure of each angle.
There's some key stuff going on here. First of all, a lot of times people, you notice that ratio has 3 numbers. A lot of times people think it's just a comparing of 2 numbers, but
Correct.
we can have what we call an extended ratio, which takes these to 3 to 4 to 5. We're still going to have to multiply them by the same amount to get where we're going.
That's a good point.
And by the way, what's another key word that I see in there
I
that you see?
see angles.
Angles. I think we got to
Angles.
remember angles. Some of us are thinking sides, and I know on the Facebook problem of the day answers this time, some of you were going with the sides. This is the angle, so let's talk about them. Let's see what we've got going on here, all right? And here's the picture. And for those of you at home, go ahead and pick that thing out, draw a little triangle, and let's talk about it. 3, 4, 5. There is an angle. There is an angle. And Gary, I think that one looks to be the smallest.
It does.
And you know how I know that? Because the smallest angle is opposite the shortest side. And this side looks really more like a short side versus the other two. All right, so finding degrees. I like to think of it as 3 times something, right, that we need to do. Oh, by the way, I guess we need to know...
How many degrees are in a triangle?
Yeah, that's a very important moment. So let's go with 180.
180.
I think they still teach that around, don't they?
Half of a square, half of a rectangle.
There you go. There you go. So what we're going to do, folks, we're going to say, 3 plus 4 plus 5 does not give us 180. You know that. I know that. All right. So let's do a little finagling with this, we'll say. Let's write our ratio. You got it there at home. And what we're going to do, we're going to open this up a little bit.
Okay.
I'm going to say, hey, I've got to multiply it by something. I just don't know what. And then I need to do the same thing with the 4, the same thing with the 5. And you mentioned it. What is it about the 3 angles? What do they do together?
They have to add up to 180.
Well, I can do that. Put a little plus sign here. Okay. Ratio action here going, equaling to 180. I think we're set. Everybody set out there? Everybody got your problem ready to go? Now, here we go. Oh, they're like terms.
They are, so we just add those up.
Oh, we got a bunch of x's. We got 3 of them, we got 4 of them, we got 5 of them. Put them together, we got 12 of them, right? So 12x equaling to 180. Boy, I hope I made this thing come out even. Want to check calculator on this real quick, guys. Let's go there. I think it should work out, but for you who are the doubters out there, we will take care of you. And we're dividing by what?
12.
12. I want to go for 15, am I right?
I think it is.
You got it. X is 15. So some of you are going like, all right, is that our angle measure?
That is not. That's the value of x, the multiple.
Absolutely. So what we're interested in is what 3x, 4x, and 5x. Now, by the way, we went ahead and decided that was going to be 3x. We'll put our 4x. How about it? 4x up here? I think 4x looks good up there.
Yeah.
And we'll
5x.
make that become 5x. So now you can get a nice visual on what's going on. So let us see what happens when we multiply by 12.
15.
No, by 15. We've already divided by 12, haven't we? All right. So 3 times 12, what do we got?
3 times 15 is 4. That's 45.
I'm stuck on 12. I don't know why.
That's what I'm here for.
45. That's why
Yes.
you're here today. Yeah, everybody knows that. And 4 times 15, let's go for
60.
60. 5 times 15.
75.
75.
Just increasing by 15 each
Oh,
time.
each time, absolutely. And add them up. I think they look pretty good to make 180. So it's easy check, easy way to go. And we could have had a variation like maybe asking what's the largest angle, the shortest, smallest angle, so forth. But yeah, folks, 12 divided into 180. We got it down, and we get that 15. That is just part of the answer. Here is really where we want to go. All right. Okay. And speaking of where we want to go, I understand we have a caller waiting for us on the line. So welcome to Mathline this afternoon. Who are we talking with?
Robbie from Blount County.
Robbie, Blount County.
Robbie.
Good to hear from you today. How are you?
Pretty good. How you doing?
Oh, doing well, doing well. What kind of great problem have you got for us to look at today?
Okay, well, I don't really have a problem, but it's more of a question.
Okay.
So I'm in pre-cal right now, and I'm studying, I'm graphing cosine and sine functions.
Okay.
I understand amplitude, translation, and period. Okay, but I'm kind of struggling with shifts. I was wondering if you could give me some tips on just how to tell what the shift is just from looking at the graph or the.
Okay.
Yeah, just looking at the graph.
Gotcha. How about, and Gary, can we go maybe use the calculator here just a minute? Let's clear out this thing.
We'll give a visual representation.
Yeah, and Robbie, this may help you see where we're going here, all right? Now, do you have a graphing calculator at home with you?
Let me see. Yeah.
Okay. You pull out along with us here, because when we start looking at some of these graphs, it makes things a little bit clearer. And Gary, I'm going to have to be refreshed on my memory here. We need to, we're going to be putting this into degree mode, right?
That makes it easier to
Let's do it in degree mode. All right, we can keep it radian mode, but let's go with degrees here. Or will it make...
I think it shouldn't make a difference, but let's go with the degree mode.
Okay, we're going to go with degree mode. We may switch off here in the middle here, all right? So, but Robbie, on there, we've already got it mapped on degrees, and right there it is, folks. And the radian could be a possibility, degree could be a possibility. We're going to go with degree and see how things work, all right? Because I'm thinking with the radians, we're going to be going between, what, 0 and 2 pi. Let's do radians.
Okay.
Let's do radians, okay? Because I think that's probably what you're looking at.
Yeah.
Yeah, okay. So let's do the radians. And what I'm going to do is we're going to go to the window. And basically what I'm going to do, the minimum here, I'm going to go with a negative 2 pi, which is going to come out to what, about negative 6.28 roughly. It rambles on. It's irrational, all right?
Wait, where it says x minimum?
Yes, x minimum, we're going to go with 2 pi, negative 2 pi. And let me get my pi on here. Oh, that could be a good song, couldn't it? Get your pi on. Our maximum, let's go with positive 2 pi.
Because think about it, Robbie, if you understand the amplitude like you say you did, then think about that y is going to be how high up will that cosine go? Or how low will it go on the graph? What's its amplitude?
Second pi here. Now, what I'm going to do is just to expand a little bit for us here, I'm going to leave the x scale, I'm going to let it be at pi, or pi over 2. Let's do pi over 2.
Okay.
I think that's a cool place to go. So let's do pi over 2. So we have second pi over 2, which is divided by the way, folks. Now, our y minimum, that's kind of big and brassy there. Let's go with a negative 3. Run that absolute value down a little bit. And how about a positive 3? And we'll leave the scale at 1. Okay. And so let's go to the y equals. All right. Let's put in sine, first of all. Let's just put in sine, and we'll put in x, lack of anything better. And let's see what happens when we graph that.
I'm sorry, what did you put in for y equals again?
Oh, y equals, let me go back there for you.
We did the sine function.
Yeah. And it's a wave, that's what we want. There we go, just y equals sine x, and I noticed mine didn't completely hit that other parenthesis, but you can do it without it. It knows what it's doing. But there we go.
Okay, yeah.
So there's our quote parent graph. All right. And notice how it's acting, how it's behaving. And if you go to, you said you know what to do with the amplitude, right? Yeah. Amplitude means we're going to put a number in front of the sine. So let's suppose we put in 2. And let's go one notch. We're going to keep both graphs there because I like to see how they behave.
Especially with different colors on this one.
Yeah, and this coloring really helps out a lot. Let's see, we'll put a sine and we'll go back to x again. And close that. And what that should do, that should raise and it should stretch it out, basically in a kind of vertical style. Yeah.
Make it taller.
And there you go, there's the red, and that's exactly what it's doing. Okay? So that's what the that's amplitude right there, okay? Now let's talk about the period inside. In other words, how fast is this thing going? Right now, what is the period per se? It looks like it's taking, get right there. It looks like it's taking,
2 pi, right?
it looks like 2 pi to get back to where it
repeating.
started, right? Before it repeats. Because folks, we're looking at a cycle here. That's what a sine wave does. It basically repeats itself, but it sets up a nice pattern and it just repeats. And that's, we have a lot of physics that deal with sine waves and cosine waves and those kind of things. So let's see, let's go back to y equals and let's throw one more in on it. Let's put in the sine, and we'll put in 2x this time. And let's see how that acts, because we already know what happens. We got red, here comes black. And what just happened, it made things move, I like to say, it makes it move faster, so to speak. But you still got the same amplitudes that you had with the blue, but all of a sudden you're squeezing your curve together much more. The cycle's still there. The period this time is what, only pi?
Yeah, it'd be, it's pi.
So that's how you're getting your period going there. Gary, keep me honest on these things. And if you were to shift, okay, if you were to shift, that's our next level here. We'll go back to y equals. And can I go ahead and let go of number 3 there? Can we do that?
Yes.
And because we get so many on here, it becomes a little confusing. And I'm going to go ahead and get rid of number 2 because we're going to show what happens on a vertical shift and also a horizontal shift. Let's see, go back up, we'll clear. And let's hit y2 there, and we're going to pick the same function. We're going to say with sine, okay? And this time, we're going to say x plus, how about it, pi over 2 maybe?
Pi over 2.
Let's do x plus pi over 2 since we're in this radian mode. So we'll put x plus, hit that pi.
Just like the others, we're going to look and see how's this graph compared to the original.
Right. And you're going to see, this is where we're going to look at, looks like it's going to move, okay? It's going to move horizontally. Let's check it out and see how it looks. You've got the blue coming back at you. And the only thing we changed this time was, and see what happened? It basically made it shift. Now, we may ask, when we look at that, you ask yourself, what did it shift left or shift right? Because it looks like it's a repeating curve, isn't it? But usually when we look at a plus 1/2, it's just like we're looking for the 0 in that parenthesis to happen. So we're saying that x is going to we're shifting to the left. We're shifting that pi over 2 units. And if we put a 1/2 on there, it would be a little more obvious without the pi over 2. Does that make sense to you there?
Yeah, all right. So if it's positive in the equation, it moves to the left. If it's negative, it moves to the right.
Absolutely.
Correct.
That's the way it works, yeah. And there again, we hit it right where it moved it basically to the middle. You know, so I mean, it's going to look the same whether we'd put a plus or a minus on that. But if let's say we would just put a 1/2 instead of pi over 2, you would definitely see a distinct difference between those two values. Does that make sense?
Yes.
Think about
Now, when the sine curve is shifted over, it kind of looks like a cosine.
It does. Actually, that becomes, and you'll find out, you know, there's some of these values that are going to actually be called trig identities, which you're going to be looking at, and that may be one of those you'll be proving, or showing that, hey, you do get the exact same value. But physically, I think when you look at things physically and can use your graphing calculator in this manner, it really helps you see and get the idea based on where you started, which was our blue, then what happens when you start doing some of this doctoring to the curve. And
I honestly didn't. Sorry.
No, go ahead. Go ahead.
I honestly didn't know you could graph cosine functions on here. I thought you could only graph equations.
Well, and actually this is a function. It's an equation in its own right because you got the y equals. And just like if you had y equals mx plus b, which is the slope function, you get a linear graph. But here you get this lovely curve, and the radians are where you really want to go on this, because otherwise we're talking a negative 360 to the left and a 360 to the right, which hits kind of crazy when you're doing the degrees. All right, so does that make all sense to you?
Yes, thank you very much.
Done good. Thank you.
Thank you for calling. Great question.
Yeah, absolutely. And that's where it's nice to have two people here to take care of those together and keep me honest, keep you honest. We're all staying honest. So some of you go like, whoa, that was pretty heavy. I want to go back and address our problem of the day. We're not going to bring it back up here, but just to tell you, one of our Facebook folks did a trig number on this, okay? Use the trigonometric ratios, which, by the way, we are going through slowly piece by piece on the Friday shows if you want to find out a little bit about just basically what that sine, cosine, and tangent is in terms of right triangles. That's what we're going with right there. Now, that's a whole different ballgame where we did the radians and such there beyond. But it's just amazing what you can do with the trigonometry. Anyway, one of our viewers, I believe, Mark may have done this on, and I think he was looking to the 3-4-5 ratio and made that the sides. And he got angles of 36 point something, which basically came out to 37 to the nearest degree, and 53, which would be correct if we had the sides in that ratio.
Right.
But just remember, folks, just because sides of a triangle are in one ratio does not make the angles fall in that way. Absolutely not. Look at your 30, 60, 90 situation, because one is the smallest, shortest leg is half the hypotenuse. So there's a 1 to 2 involved. So again, we digress a little bit, but just little cautionary things there. But I love it. People are already thinking about trig.
That's right.
To apply it anytime they can. Just be careful when it does apply and when it doesn't. So, speaking of which, we've had a great call. We wanted some other people to call in, all right? That number, 844-686-2378. My friends, we want to hear from you, all right? Robbie's giving us a call from Blount County. We appreciate it. And now we need to hear from you guys. And in the meantime, I think we've got a little message from my friend Bert. And let's see here. This is a little question Bert asked. Yeah, you said, is that like Bert and Ernie? Yep, it is. But we aren't together on Sesame Street, but we occasionally get on the opera stage together. So a good friend of mine from Maryville area was a retired professor of voice and choir and all sorts of great musical things, a musical professor down at Maryville College. But he asked this question: is there a simple way to understand rational numbers versus irrational numbers? And some of you are going like, I just thought all numbers were irrational. So there is a nice thing about that. So Gary, first of all, let's just talk about what do rational numbers look like?
Well,
what can we think of them as?
You know, since we've already worked with ratios this whole week, you know, I see the word ratio right inside there. The first
yeah, with rational, we got that word ratio. So guess what? If we can make ratio of what, two integers?
Two integers.
Like an A over B, we'll say. Then we've got a rational number.
Any number that can be written in that form.
Oh my gosh. So, okay, so let's get me straight here. If I were to look at the number, so something like 2/3, definitely.
Absolutely.
Rational, okay? What about the number 5?
Can I write that in a form of A over B and not change the value of it? I could write this 5 over 1.
Okay, all right, so we could come back and use another rational expression, would be 5 over 1. Gotcha. All right. Well, all right. Can we have decimals in there?
If we could write it as a ratio, what about 0.5? 0.5 tenths.
Okay, 5 tenths, 0.5. That would be, well, that'd be like, but 0.5 over 1 isn't a ratio. Well, it is a ratio, but it's not a two integers, is it?
But could we write it as a ratio of 2 integers?
Oh, yeah, we could. It's 1/2,
It's 1/2.
All right, so there we go. So, Bert, there's part of the game. In other words, we can eventually get to some sort of a nice 2-integer ratio of 2 integers here.
Okay.
Now, what about the irrational? I always think of a square root of something that just doesn't fly. Now, if I hit the square root of 4, that's equal to what? 2 or -2, either way we want to look at it. But either one of those is, just like with 5, we can put a 1 under, right?
We can write it as a ratio, yes.
Okay. Now, what about, let's just take, since we got 5 there, what is that?
Doesn't make sense.
It's irrational,
It's
isn't
irrational.
it? Let's see what the calculator tells us. I always like to see what the calculator tells us because it's going to tell us more stuff than I could ever remember about the square root of 5 or would ever want to remember about the square root of 5. Like, how many places will it go with us here? Because, my friends, there is no pattern. There is no repeating. There is rambling.
Right.
And basically with no direction, no pattern emerging, no repetition, no repeating, no termination, that's for sure, because it's still going. So that's what we call an irrational. It cannot be written as a fraction no matter how we try. That would not come out even as a fraction.
Well, Ernie, you mentioned Bert. He does some things with music.
Yes.
Can I bring up that?
Go for it. Yeah.
Well, there's some thought that Pythagoras,
Our good old friend Pythagoras. Pythagorean theorem.
He was a lover of music himself. So he found the relationship between notes that were pleasing to the ear that made sense.
Would those be maybe
Rational numbers.
Rational,
They can
okay.
be written
Gotcha.
as whole number integers, two
begin to
different
wonder
notes.
if it was the other way around.
But
That's
there's
scary.
certain notes that didn't make sense, that weren't pleasing to the ear, and they
Okay.
couldn't be written in terms of the interval between two notes, could not be written with whole numbers.
Okay.
So they didn't make sense, they weren't pleasing, so they were irrational.
And then he translates that from his music standpoint, compares it,
To triangles.
works with the triangle.
Yep.
Wow. So, folks, yes, there is a link in the math.
Mm-hmm.
And those of you who love music out there, it is. There's a lot of mathematics going on there. Not just that you can count to 4 in a measure or something
right.
like that. Try to keep rhythm and stuff. But it is definitely some good things. Let's let's do this one.
Let's stay with the rational numbers.
Yeah, let's do one more quick thing since we got going on rational and irrational. Let's take a look real quick. We're going to look at the two numbers, 7 and the square root of 7, which y'all are going like, we know that 7's rational, and we know what? That the square root of 7 is irrational. And you go like, and let me point out to you, real numbers, they are real. They're both real.
They're right there in front of you.
Even though you're going like, but we can't seem to find that square root of 7 exactly. Well, we sort of can, because when it crosses that number line on a graph, it hits it at the square root of 7. There's a place. There's a place for it. So it is real. It is real. It's just one of those harder things to figure out where it is. Now, what about 7? When I talk about the subsets of the real number system, that's like, besides rational, we've said they're real. Okay, we've got for 7, we've got real, we've got it rational. What else can we break it down into, Gary?
Well, it's an integer.
An integer, yeah. Now let me dispel another myth that I find with my students. Some of them think that the integers have to be negative. It's not. They are negative, but they're also positive, and they also could be 0. So it is an integer, the number 7. Okay, we can write it 7 over 1. We've got it as a real number. When we learn how to count, we have a group of numbers called the natural numbers. And then what happened after that, we ended up with whole numbers when we added the 0 to the game.
Right.
And then we got to the integers when we threw in negatives in addition to the other guys. Now over here on the other side, we got this lonesome little square root of 7 hanging out. What happens there? Well, they're real, because they're somewhere.
Still real.
They're real. And what's the other side of it? If they aren't rational, they've got to be irrational. And once they're irrational, all this other stuff just kind of goes away.
That's exactly
They're
it.
not going to be integers. They're not going to work out to be countable, counting numbers, natural numbers, and whole numbers don't work out either in that case. So there's your deal, my friends. Bert, I hope that answered your question. And also, we appreciate the allowing us to think about some music in addition to that. Hey, we got, I don't know if we got time for the Hey Math line, but we will save that one for tomorrow, I guess. Let's do one quick thing about benchmarks, all right, to finish it off. By the way, folks, call us if you still got some time on you, would like to call. Let's look at it, 844-686-2378. Those are all rational numbers, by the way. We want to hear from you. It's a rational thing to do is give us a call, all right, just like Robbie did earlier today. So we've got 3 fractions here. Gary, we're going to look at them and say, can we put them in order from the least to the greatest? We got about 2 minutes left to work through this. Tell us some shortcuts here.
Well, without thinking in calculations, let's just think about it, visualize. In terms of, we've got a half.
Can I put a line down here?
So I have a half of something. So we'll start with that one.
All right, because we think of really a half being, all these are between 0 and 1. So let's just say here's a 0, here's a 1. Some of you are going like, but Ernie, 0 should be in the middle. Well, it's okay. It's a number line. It keeps going on forever and ever, right?
But if I got 3/5, that means I have 3 out of 5 something. And 3 is a little bit more than halfway of 5. So it's bigger than a half.
All right, yeah, that's true. Because, yes, and sometimes we can quickly hit those decimal forms of that 3/5. So here we are at 1/2. So 3/5 is, it's a little bit more than halfway. Yeah, absolutely. So somewhere over here we got 3/5. And then what about 4/9?
Well, if I think about 4 out of 9, if I've got $9, 4 is a little bit less than a half of it.
It's a good point. Yes.
So it's a little bit less than a
So
half.
I'll be looking for 4.5 to be actually 1/2. So we are definitely over here So in putting it from least to greatest, it looks like we started with what? 4/9?
4/9.
Kick along. How about it? We go to 1/2, and then we hit 3/5.
You didn't have to bust a calculator.
I'll tell you what, we
Look at
didn't even have to look for a common denominator, which, by the way, that would be like 90.
Ooh, that
So
would be
aren't
rough.
you see why we want you to learn a few benchmark fractions and also just a little bit of number sense to go along with those that aren't just perfect benchmark fractions.
This was a good day.
Yeah, good day here today, Gary. Thanks for being with us today once again. I understand you're going to have some busy stuff to deal with
Correct.
tomorrow, so y'all get stuck with me tomorrow, but we'll be back. We're going to have some good stuff again, and also get back in the swing of you guys calling us and stuff. We had election day going on today. We're going to find out all the winners tonight, and we're going to find out what those percentages are. So take close attention.
That's right.
It's mathematics. And again, thank you for tuning in this afternoon. And Gary, thank you again.
You
We'll
bet.
see you again next time
Next
when
time.
you tune in to us, right, tomorrow, and we will see you then.